Hello everyone. Since I am relatively new to this company, I decided to use this occasion to introduce myself. My name is Krzysztof Kudrynski. Together with Bartlomiej Pietrzyk, we are going to talk about content-oriented picture resizing. We both with Bartek work in machine-assisted updates division. Bartek with Bazinga team, he works on height and gradient. And me with Roman team, we work on traffic flow restriction, maneuvers, and roundabout detection. Today we are going to talk about seam carving. Seam carving is a novel technique for content-oriented picture resizing. And although resizing images seems very unrelated to what we do in the company, in fact it has a lot in common because the algorithms behind seam carving are almost the same as those used for routing in digital maps and many other applications which you probably experienced and had contact with. So to warm up, I'm going to start with a bit off-topic example. So let's imagine we want to find the shortest, most optimal path from city A to city B. For this example, it's from Dziewuliny to Kobyłki. And for this purpose, we will generate a graph with vertices and edges. For each edge, we will assign some weight, which may be the combination of distance, road class, traffic intensity, and so on. And then we are going to construct the shortest path tree and choose the shortest path to the destination. So this is how we would probably act when we want to find the shortest way in the graph between the cities. And in fact, we will use a very similar methodology in the topic that we are going to present today. What is the aim? What we want to do? We have some picture and we want to resize it in such a way that most important contents, most detailed things are preserved in the photo, but it is done automatically. So we are going to talk about this. We are going to tell how we use graph for this. We will show you our implementation. And in the end of this presentation, we will provide you with, I hope, very interesting examples. So wait patiently till the amazing comes. So okay, what is the problem? Suppose we have a photo and we would like to send it for the contest for the most beautiful photo where we could win a lot of money. So we choose our best photo. If we don't have any photos from holidays, we took one from the office and we try to send it to the contest. The problem is that the required dimensions for the contest are different than the ones that we have. So what are the options? We can resize the photo in such a way that we just downsample it and interpolate. As the result, we get Bartek, who finally looks like he always dreamed to look.
That's me.
On the other hand, we have myself, but now you cannot appreciate my recent gym. The most dramatic thing, however, is the board with the vision of our company, because the font is no longer standard. The conclusion is simple. With such a photo, the contest is unwinnable. What are other options? Of course, we can just crop the part of our picture.
Hilarious.
And you may agree or not, the picture looks even better now.
Hilarious, Krzysztof.
The problem is with the distribution, so the contest will be spoiled. Maybe a more sophisticated trick would be to find cross-sections of the lowest variance that will flow through the picture and remove them out of the picture. And as you can see, the resulting picture is almost perfect. The only problem is that Bartek's right hand is gone and he said it's useful. So that's how we come to the solution, which is the main topic of our presentation, what we can do is we can find nonlinear seams of lowest variance or energy and carve them out of the picture, which is called seam carving. How we are going to do this? Let's, for simplicity, assume that our contest picture is now 10 by 10 image, and we construct a graph in such a way that every pixel corresponds to one vertex. And then the graph has such structure that a single vertex points with edges to 3 vertices that are below it, or in other words, every vertex is pointed by 3 vertices that lie above it. The next thing we do is we add 2 virtual indices in the top and at the bottom. And finally, similarly to the case of routing in digital map, we assign weights to our edges. And since we would like to preserve content of the picture which is most detailed and maybe resign of the content which is plain, we define energy function for the picture, and we want the energy to be very small when there is not much detail, so the picture is plain, and there is a lot energy in places where there is a lot of variance. There are a lot of ways to realize such function, but maybe one of the most easy ones and which will serve our purpose is just sum of gradients in x and y directions. So we just make the difference. And of course, we add this value for all 3 colors if we use color space. This is, I'm not sure if it's visible, maybe a little bit. This is the energy function translated to pixel intensities. So you can see for our contest photo how the picture will look like. And we assign these energies to the edges of our graph. And then we are able to find the shortest path in our graph from the top to the bottom and carve it out from the picture one by one, as long as we would like to have the image that is required. So now Bartek will tell you what is the elegant way to implement graphs. And then based on this general info, I'm going to follow on with how we used it in our particular case.
Okay, so first of all, welcome everyone. Thank you, Krzysztof, for this fine introduction of myself. Okay, so while we were doing online education course on algorithms from Princeton University that is freely available on Coursera, we stumbled upon this clean and elegant way of implementing an edge-weighted directed graph, which in turn allowed us to bootstrap from this to our solution that we are currently using in our seam carving application. So the edge-weighted digraph is assuming that we know the number of vertices inside the graph. The interface is pretty clean and simple and sufficient to do all the operations on the graph. So we can ask for the graph for the number of edges, the vertices, we can add directed edges, we can ask for the adjacent edges to the supplied vertex, and we can take the list all of the edges that are composing the edge-weighted digraph. As for the edge structure, it's also simple. It contains both of the nodes and the weight of the edge itself. So, inside it's implemented as a single array where the indices inside the array symbolize the vertices inside the graph, and the values that are inside the array are the bags that contain all of the adjacent edges that connect to the supplied vertice. So for example, for 2, we have a bag that contains a vertice 2, 7, and 34. So we got a connection from 2 to 7, and the weight is 0.34. As for the shortest path algorithm, it was separated into a separate object. The object is being constructed with on a given edge-weighted digraph and a point to which we want to calculate the shortest path for the whole graph. And inside, it is being represented as two arrays of integers. Well, the first array symbolizes the shortest, the next vertice on the shortest path from the given point to the point on which, for which we calculate the shortest path. So, for example, we want to calculate the shortest path for 2. So we take the indice of 2, and under the inside the array, under the indice 2, we have a direct connection from 2 to 0. So 2 is connected directly to 0. For example, for 3, sorry for my handshaking. For 3, we have a connection from 3 to 7. Under the index 7, we have connection from 7 to 2. And under 2, we have a connection from 2 to 0, which symbolizes the shortest path from 3 to 0. The second array contains the distance that has to be, well, it contains the distance from the given point, 3, to the vertex 0 for which we calculate the shortest path. So the idea is plain and simple. And how do we calculate all of those values? Well, this is the next slide. Krzysztof will talk about it.
So if we have these two arrays, we are able to easily get the shortest path from any point to the source. How we compute it? Of course, we can use a famous Dijkstra's shortest path tree. This is not a lecture algorithm, so I'm not going to explain it until the last person of you will understand it, but probably most of you have heard about it, and many of you are experts about this. Anyway, I want to give a short overview how it works like, to later show you how we contributed to this for our particular case. So first, we initialize all the distances to infinity. As on the beginning, we don't know how far away are all the vertices from our source. And of course, we initialize source from 0 to 0 to 0. Then we create a minimum priority queue to which, and we iterate over all vertices starting from the source. For every analyzed vertex, we add to the queue all the vertices that it points to, and the priority is made from the distance. And we follow by the shortest distance. So we remove from the priority queue on every iteration and find the next iteration that we want to follow. The important thing is that what we do is we exchange the value that is actually here, it was infinity in the beginning, with the new value if it is smaller than the one already stored in distance 2. So for this example, we will just, for 2, we will put just the distance to 2. Next iteration, we will, the first on the priority queue will be 4, so we will put 4 and the distance to it, and so on. So thanks to using priority queue, we make sure that we go from the source to the most distant point. That's why we are sure we'll only go to each point once, and we will have the shortest path tree. It might seem confusing for people who hear it for the first time, but there's a lot of literature on this, so I'm not going maybe to convey this idea too much. Anyway, what I want to say is that it's very hard to compete with Dijkstra's algorithm because it is quite powerful in the general case, but in our particular case, it's possible. And because we have a very specific structure of our graph, And we can capitalize on that. First, what we know is that our graph is acyclic. There are no cycles inside. It's top-bottom, it's very well structured, and intuition tells us we don't need to use a single array, but the table will be better because it's intuitively, it's a picture. When we know we have a table, we don't need to store the adjacency array because from the table itself, we know the adjacency by the indexes. What's more, by every step, we don't need to store entire shortest path through. We don't need to know the shortest path from this point to source and from this point to source in the end. We only need to know the shortest path from top to bottom. So we don't need to store all the time all the information. Finally, what is very important is that for a given vertex, the cost to get to it from the vertices above is always the same and is equal to the energy of this pixel. So we don't need to store for every edge the values of weights, but we can store it inside the vertex. And having this, there is one more simplification which we can make. When we know the shortest path to free adjacent point, it means we immediately know the shortest path to this point as the shortest path of these three shortest paths. Clear, I hope?
It's clear.
So this is what we can capitalize on, and now what is our particular solution? So similarly to Dijkstra's algorithm, we have the edge2 table. Well, here it's table. It was previously the array. And we have a distance to table, but now it does not contain all of the vertices, but only one row. And what we are going to do, we are going to update the distance to parallelly for all of the vertices in a single row. So in the beginning, we initialize it to 0 as the distance from any of these points to the source node is 0. Then what we do, we position ourselves at the second row, and we find out by which index we need to go from every index to have the shortest path to the source. And in the for the first time, it's trivial because we can just go straight on for every, because they are all the same, these values. So from index 0, we go through 0. From index 1, we go through 1, and so on and so on. And that's what we put in the edge 2. Then we want to update the distance to. So how we do this? For index 0, we put the cost to actually get to this point, plus the cost to come to the point which is on position 0 here. So we add this, and we update the distance to. Then we again update the edge 2. Now it's a bit less trivial because, for example, for this index, we cannot go through 0, we need to go through 1, which is shown here, and so on and so on. Now we again update the distance to, and as you can see, the distance to value is cumulated, so we can forget about all this because we know the distance to the shortest distance to every point from this. And we move until finally we get to the point where we have the shortest distance to go to the last row, and from this we choose the shortest of the shortest distances, which is 38 or 38, it doesn't matter. We find which is the index of the shortest distance, and we know that from the top to bottom the shortest path is 38, and we will finish in this index. And now we can follow. From 6 we go to 6, go to 6, go to 6, go to 7, go to 6, go to 5, and so on, and we will find the shortest path, which is much simpler than Dijkstra's algorithm because we do not need to make relaxations all the time, but we can compute it parallelly. And of course, we analyze more than one seam at the time, which takes a lot of time, and there is still a lot of possible optimizations, and this is what Bartek is going to continue on.
Okay, so now let's get to the nitty-gritty stuff. This is the implementation. So the first version of our application was developed in quite a reasonable amount of time. I believe it was 2 days, I think, that we got to the reference version. But it suffered one particular problem, and it was performance. It was unsuitably slow to be shown to a live audience. So we had two solutions. Either we make it faster, or we leave it as it is, and while we will be waiting on the seam carving process to finish, Krzysztof will show off his amazing dancing skills. So we went with the second solution, with the first solution, sorry. With the first solution, and we started to optimize this. So, to show off the optimization that we did, I will be using this famous picture of the flower, the rotor with red blades. Oh, sorry. So, our first identified problem was gradient calculation. And the problem was obvious that it was taking too much time. Well, by the way, we used the profiler to identify it. The first thing that came to our minds, how to make it faster, well, we could add additional power to the machine, but we all know that we won't be able to we won't be able to bring a server here, just our desktop machines. So we knew we have to use multi-threading, and to our success, well, calculating the gradient is a process that is independent for every pixel. So we can do calculation of every gradient point in a separate execution thread without running into race conditions. So we spawn n threads, where n is the number of available cores on the machine that we will operate, and process the gradient calculation in stripes. Every stripe processed by its according thread. So this was the first major improvement over the initial version. The second problem that we identified was, well, to display it in a rather simple manner, we used swing components, and the image was represented using buffered image. Well, the buffered image is all nice and dandy, but it's, for our purposes, it had one particular flaw. It didn't allow us to manipulate on the memory in bulk, with bulk operations, and we had to use setRGB and getRGB methods, which are particularly slow if you get to a rather big image. Well, a full HD image was enough to make the system cry. So what we came up with is a twofold solution. Well, for example, we identified a horizontal seam, and while doing this horizontal seam carving, we identified a seam, and we know that inside the buffered image, the image itself is represented as a single array that contains consecutive rows of pixels. So after analyzing the image itself, we notified that we could reconstruct the image without the seams that we had to remove using plain array copies. There's a monstrous do-while loop, the first do-while loop that I ever wrote to solve any problem, that calculates the indices of the seam, of the carved out pixels, and does the appropriate array copies to move the data to a new destination array, which in fact would lead us to a new buffered image. So this was pretty straightforward and gained us immense performance improvement. But the problem was while trying to do the vertical seam carving. Well, the problem here was due to the row alignment of the image inside the memory, we couldn't in an easy way calculate the array copies that we had to do. So what we came up with was we calculated the lowest index of the horizontal seam. So in our case, this would be 5. Then we did a bulk array copy of this whole fragment. Then we knew the position of the seam, well, column-wise. So we knew that those 2 pixels, this one, had to be moved 1 row up to get the full image back inside the destination area of the memory. So after this process of moving, we were left with the last array copy that would move the rest of the image to the destination position, and voila, we have the resulting SIM card imaged. So, the last take on the grading calculation improvements, which was still slow even though using multi-threading, was that, well, we identified that when we do SIM carving and the image gets one row smaller, we really don't have to recalculate the gradient in those places. Because the neighbors of those pixels don't change, so the gradient also won't change. And this led us to a conclusion that we have to do a local gradient recalculation, and the marked pixels are the ones that have to be recalculated in the destination gradient image of the picture. So after creating the resulting image, we do the recalculation process locally, which also was about, I don't know, 10 times faster than, or even more, I think, because we are calculating just two stripes of pixel data in comparison with the first approach that calculated the gradient for the whole image. Well, the multi-threading is still there, but because we have to calculate the first initial gradient for the picture. So the code is still used, but just for the initial reading of the image. So those three performance improvements made the application suitable for demoing.
Which is going to happen now. So whoever is sleeping, please wake up, because now the cherry on the cake, the examples.
And the crowd goes wild. Okay, so our favorite tool, Eclipse.
So the first will be our contest photo, which we
Yep.
want to be as beautiful as possible.
Okay,
And this is our wonderful graphical interface.
Yep.
And we want to make it smaller.
So we are starting to SIM carve it. So the process looks like this. Okay, I won't be moving it any closer because it will damage the,
Yes,
the
now
font.
when we continue, the SIM carving algorithm will become more and more aggressive, and it will start to remove SIMs which are of high energy, because the low energy SIMs
I think you can
does not exist.
I
We will
think-
show you in the end some
I think
nicer
we can
things.
I think we can do more pressuring just to show that
Okay.
it won't crash.
Okay.
If you squeeze it anymore. So yeah, unfortunately it's taking me apart.
Well, the most important details remain on the picture.
Oh yes, the obvious ones. My hand.
Okay, now a second example,
The
very
lighthouse.
nice.
Okay,
This is very useful, in fact. You will see in the last example. It's very useful.
okay. So I think we
Yeah, I
we
think
can
it's
leave
okay.
it be.
You agree? Show us the next. The next one is I don't remember, but it's very nice example.
Shanghai.
We want to make Shanghai a little bit more crowded, because it's in.
They have too much free space.
So you can see how the spaces in between buildings disappears first. Yes.
Of course.
We can make them shorter, of course.
Do we want to make them shorter?
We can do it. Come on.
Okay, we'll try.
You can see.
Okay.
So it's okay for the ones who live in the proper levels, you know.
Shanghai.
Now our TomTom banner.
Oh, this one is nice.
Yes, it's very nice. We want to, for example, show it on the mobile phone, and we want to keep the most important thing, which is the road, with not much changes. You can do it in the other direction as well.
Okay, so we'll try to compress it the other way. Please no null pointer.
Yeah.
Okay.
Well, there are some changes, but generally the most important details stay the same. The next example. Oh, this is useful for the guys, which will show the winner of the contest.
Okay.
I'm just kidding, of course.
No, yes, you
but
are.
they want to show the last winning shot, and if we
Did he got them
from the bottom, from the bottom.
from the bottom?
Yeah.
Okay.
So it's going straight for the tank, no?
Did he got
And
them?
now it's.
Ah, no.
So we don't encourage using our algorithm for this because it loses a little bit of geometry. It doesn't matter too much. We will show you that sometimes it might even help.
Okay, so the last and cardinal example. Was
So
an
there are
offside?
sometimes situations when you quarrel with your friend that there was an offside or not, and he says there was an offside, come on.
Okay.
And you
was
say
there
no.
Was there an offside or not? Let's see. Was it? Was it? Nah, there wasn't any offside.
Okay, I think it's enough.
So, okay, so that's
Yeah.
the live examples.
That's everything. So maybe let's come back to
Okay.
the presentation to show before and after effect, because this is what makes our imagination work better. So this is before and after. The first photo. What is very interesting, you can see the floor, yes? This is the place where the seams were all flowing out of this, and it looks funny, but well, the last corrections you may make manually. This is the second picture. The third one. Oh, this was not shown. This is something if you use Facebook and you want to make your the first photo.
Well, but the
Timeline
the
photo.
clouds
Timeline
look really
photo.
peculiar
Timeline photo.
here.
Timeline photo. This is the TomTom banner page, and this is an offside.
No offside.
So, this was our presentation. Thank you very much for your attention.